The second method that we can use to charge an electroscope is what we call by induction. How does that happen? Okay, what we do, just to give you a preview of what we are going to see, is this is going to be my electroscope. When it is neutral, the vanes are close to each other, and we have charges balanced throughout the electroscope. Now, what we do then is approach a charged rod. In this case, we are going to approach a rod that it is positively charged. Now, when we approach positively charged rod, then negative charges from within the electroscope, since it's made out of conducting material, are going to be attracted to the top. And so that's going to leave the bottom with a net positive charge, so the vanes are going to be apart. Now notice again, we are not touching it, we are just approaching the charged rod. Now what we do next is touch the electroscope to ground. Okay, this is the thing, briefly grounded. Touch it, connect it to ground or to a vast reservoir of charges. That's the purpose of the ground. So now while it is under the effect of this positive charge and those negative charges are on top and these positive charges are in the bottom, now we connect this to ground. This is usually the symbol for ground, which is, as I mentioned a moment ago, a big reservoir of charges. Now, what's the effect of that? Since this is a big reservoir of charges, these negative charges here are somewhat balanced with these. However, these are not balanced. So what's going to happen? Remember, the charges that are going to easily move are going to be the electrons, so negative charges. So whatever is going to happen is it's going to be either us losing negative charges to the electroscope or us gaining negative charges from the ground. Now in this case, we have an excess of positive charges here that's not balanced. So these positive charges are going to attract negative charges from the ground. So I'm going to have negative charges coming in and balancing these. So while this is touching ground, what's going to happen? We are going to have this condition. The negative charges on top that are balanced by the positive charges on the rod, or they are really under the effect of those positive charges. And in the bottom, where the vanes are, it's going to become balanced. So when it is balanced that way, we remove the ground. Okay, so when we remove the ground, what's going to happen? We are going to leave an imbalance in the electroscope. This negative charges on the top. The vanes are still not apart, but we have that imbalance. So if we move the rod away, these negative charges will have no reason for staying on top anymore. They are going to distribute, and the vanes are going to move apart again. Okay, let's see it. Okay, we touch. Negative charges come in. Okay, move the rod apart, and we have a net charge. So the vanes are apart. Okay. Think about the alternative. What would happen if we approach a negative rod instead of a positive rod? I'm not going to go through it. Just think of it yourself. Now, a few things to mention. What I have here, okay, you notice opposite to the case we talked about earlier, where I had the negative charges being stuck to the atoms. Look here, we have a metal with an excess positive charge. We put it close to another piece of metal. Now, this one was balanced, so the minute we approach this, look what's going to happen. The negative charges in this one are going to be attracted to this one here. So we see them all pile up on that side. And the positive charges are going to be repelled. So it's not really the positive charges moving, but the atoms are going to lose their electrons that are going to be attracted to this side. So the net effect is to have a pile up of positive charges in the other side. Now, how is the balance of charges in this other metal? Look at the way the balance happens now. It's this side that's furthest away is going to have less charges than the side that's close to the other metal. And that's because these are feeling the effect of the attraction of this negative charge, while these are feeling a lesser effect, so that's why they are further out. And notice also that as we get close to the corners, there is more pileup of a net charge. Okay, that's an interesting thing that we'll talk about briefly a little later. Now, when we did the grounding, what did we do? So we have this, and we connected this to a big reservoir of charges. Now, the negative charges are attracted to this. So these unbalanced ones are going to get electrons coming from ground that are going to balance them. You see here, we are not drawing it exactly that way. We are drawing it like if the positive charges are moving. In reality, they are not. But effectively, when a negative charge is going to come to balance one, that's like the positive charge moving. Now, when are we going to have positive charges moving? For the ones among you who are in chemistry, you have experienced, you have dealt with reactions where you have in solutions some positive ions moving. That's the full ion. Because it's in a liquid, it can move. That's the cases when we have motion of positive charges. Otherwise, a motion of a negative charge in one direction is equivalent to the motion of a positive charge in the other way. So usually we don't have motion of positive charges. Okay. Now, one thing interesting, when we have a charged object, for example, if you take a pen and charge it up and leave it for a little while, it's going to lose that charge. We will use what we call the Van der Graaf generator as a demo, but then the Van der Graaf generator is going to have an excess charge on top, and then if you leave it on for a little while, it's going to lose that excess charge. Why is it going to lose that excess charge? Just because of molecules in the air. The molecules in the air are going to, they have charges themselves. Think of the water molecules, for example. They have hydrogen and oxygen. So they have charges. So they're going to be attracted to our charged object. And by being attracted, they are going to capture some of that excess charge. And the minute they capture that excess charge, they become repelled by it because suddenly they are going to have of the same charge as the Van der Graaf generator, as the dome there. So if they become of the same charge, they get repelled. Okay. This is kind of the same idea. So what we have, if I have negative charges here, then the positives of the air molecules are going to be attracted towards it. The minute it comes close by, then I'm going to have negative charges coming in. They jump into that molecule, so that molecule is going to have an excess negative charge, and then it's going to be pushed away or repelled. Okay, this is, I thought, is interesting. I found it in an article from, I believe it was an Australian site. On average, and for a low 10% to 20% relative humidity, walking on a carpet generates 1500 to 35,000 volts. A vinyl envelope, 600 to 7,000 volts. Picking up a plastic bag from the table, look how much. Walking on vinyl floors, look how much. Bench. Okay, now as you increase the relative humidity, you reduce the amount of charge, because the more water you have in the atmosphere, these molecules are going to steal that excess charge over whatever is available. However, of course, you see that's going to be a problem with other things. High relative humidity is going to damage electronics and other things.